In the vast dark, there are more stars than grains of sand on every beach on Earth, and almost every one should have a planet. Someone out there should have said hello by now, but nobody has. We have searched for 70 years with our best instruments pointed at the sky and gotten nothing back. A planet that seemed to breathe, a gas that looked exactly like life, a signal that made scientists hold their breath. Each one fell apart under closer study. Tonight, we find out why the loudest possible universe stayed silent, and the answer is more unsettling than any alien could ever be. If this mystery keeps you thinking, go ahead and subscribe. It helps this channel grow. Take a slow breath. We are about to listen to the silence itself. Picture a single night, anywhere on Earth, and look up. What you see is only a fraction of what is actually there. Behind every visible point of light sit hundreds more, too faint or too far for your eyes alone. Astronomers now estimate that our galaxy holds something like 400 billion stars, and beyond our galaxy there are roughly 2 trillion more galaxies, each one carrying its own enormous family of stars. Multiply that out, and the number of planets becomes almost impossible to hold in your mind. Even if only a tiny sliver of those worlds sit in the right zone, warm enough for liquid water, cool enough to keep an atmosphere, that sliver is still staggering. It is billions of candidates, just in the part of the universe we can observe. Here is the strange part. With numbers that large, the laws of probability suggest contact should not be rare. It should be common. Some calculations done decades ago, using only conservative assumptions, suggested that intelligent, communicating life should have arisen many times over by now, and some of it should be old enough, advanced enough, to have spread across its galaxy already. If even one civilization managed that feat anywhere in the last several billion years, their signals, their probes, or their structures should be detectable somewhere. And yet, here we are. No call, no structure, no unmistakable signal sitting in our data. This is the heart of the problem first sharpened by physicist Enrico Fermi in 1950, when he reportedly looked at his colleagues over lunch and asked a simple question that still haunts modern astronomy. Where is everybody? It became known as the Fermi question, and it has only grown more uncomfortable as our telescopes have grown more powerful. Because the more we discover, the worse the silence gets. Every new planet we find that looks promising raises the same expectation, and every time the silence holds. It is confirmed, beyond question, that thousands of planets exist beyond our solar system. It is confirmed that many sit inside zones where liquid water could exist. What remains a mystery, a true unknown, is why none of them have ever answered. Some scientists believe the answer is simple bad luck, that life is rare in a way we have not yet appreciated. Others believe something far stranger is happening, a deeper pattern running through the entire universe, one connected to our own future as much as to anyone else's. Tonight we are going to follow the newest evidence, the freshest data from our most powerful instruments, and trace this question all the way to its darkest possible answer. Because just months ago, scientists thought they might have actually broken this silence. They thought they had found a sign, a genuine flicker of biology on a distant world. Word of it spread fast, through laboratories and headlines alike, carrying a kind of electricity that the search for life beyond Earth had not felt in years. And what happened next will change how you think about every quiet night sky for the rest of your life. To understand how disturbing the silence really is, you first have to understand how generous the universe has been with its raw materials. Stars are not rare, they are everywhere, scattered through space in numbers that defeat ordinary counting. Our galaxy alone contains so many that if you tried to count one star every second, it would take longer than 10,000 years to finish. Now scale that up. Modern surveys using deep field imaging have shown that for every star in our galaxy, there are roughly 2 trillion more galaxies out there, each filled with their own billions of stars. The observable universe alone may contain something on the order of 1 septillion stars, a number so large it stops feeling like a number and starts feeling like an idea. What makes this relevant is a simple piece of math called the habitable zone. Around every star sits a narrow band of distance where a planet could be warm enough to hold liquid water without boiling it away or freezing it solid. Earth sits comfortably inside that zone. So does Mars, barely, on the cold edge. As our telescopes have improved, we have confirmed that this kind of zone is common. It is not an Earth-exclusive feature. Thousands of planets discovered so far sit within their star's habitable band, but compared to what comes next, this counting exercise looks calm, because finding a planet in the right zone is only the first filter. The planet also needs the right mass, enough gravity to hold an atmosphere without losing it to space, yet little enough that it does not crush any chemistry trying to happen on its surface. It needs a stable orbit, not too elliptical, not disturbed by a chaotic neighbor. It likely needs a large companion moon, or a giant outer planet acting like a cosmic bodyguard, absorbing impacts that would otherwise sterilize the surface again and again. Even after all of that, the planet needs time. Billions of years of relative stability are required, because complex life, the kind capable of building a radio telescope and aiming it at the sky, appears to take an extraordinarily long road to get there. Earth needed roughly 4 billion years to go from simple chemistry to a species capable of asking where everyone else is. Every single one of these steps had to happen in order, and every single one had to succeed. Despite every one of these narrow requirements, the sheer scale of the universe means there should still be an enormous number of candidates. Conservative estimates, the kind built by cautious scientists who assume far fewer planets work out than expected, still produce numbers in the billions. Even if the true number of life-bearing worlds is a tiny fraction of that, tiny here still means enormous. So the question deepens rather than resolves. With a universe this generous, this old, this enormous in scale, the silence stops feeling like an accident. It starts to feel deliberate, and deliberate silence is far more unsettling than empty space ever could be. For decades, the search for life beyond Earth lived mostly in theory and mathematics. Then, just a few years ago, a single planet briefly made that search feel real. Its name is awkward and technical, so for tonight, we will simply call it the ocean world, because that is what it appeared to be. The ocean world orbits a small, cool star, roughly 120 light-years away, well within reach of our most advanced telescope. It is larger than Earth, several times heavier, and sits inside its star's habitable zone, the same comfortable band where liquid water can exist. When astronomers pointed our newest space telescope at this planet's atmosphere, they were not expecting much. What they found made headlines around the world within days. Hidden inside the starlight passing through that thin atmosphere were chemical fingerprints, faint signatures of specific molecules. One of them was particularly exciting, a gas that, here on Earth, is produced almost exclusively by ocean-dwelling microorganisms. For a brief, electric moment in the scientific community, it looked like we might be staring at the first real evidence of life on another world, the kind of moment researchers spend entire careers hoping to witness. This is where trust signals matter most. At the time, this detection was reported as tentative, a possible signal, not a confirmed discovery. Reputable scientists were careful with their language, using words like suggestive and intriguing rather than proof. The space agency that runs the telescope did not even issue an official announcement, a quiet signal in itself that confidence was lower than the public excitement suggested. Independent teams of researchers, working separately from the original group, were asked to review the same raw data before anyone went public with stronger claims. Compared to what comes next, that early caution looks almost prophetic. As more data came in, and more research teams checked the numbers, doubts began to grow steadily. The same chemical signature, it turned out, could also be produced by entirely lifeless processes, chemical reactions involving rock, gas, and pressure that have nothing to do with biology at all. The very feature that had briefly suggested an ocean teeming with microscopic life could just as easily belong to a chemically active, completely sterile world. This is how careful science is supposed to work. Every exciting signal must survive scrutiny, must be checked against every boring explanation before it can be trusted. So far, this one has not survived that test. The ocean world remains fascinating, strange, and unconfirmed, neither proven alive nor proven dead. What this story reveals is something deeper than one disappointing planet. It reveals just how easily the universe can imitate life without actually producing it. If a planet can fake a biological signal this convincingly, every other hopeful signal we have ever recorded deserves the same suspicion. The silence may not be empty after all. It may simply be very good at disguising itself, and that disguise is exactly what the next chapter takes apart piece by piece. The molecule at the center of this story has a long, clinical name, but its nickname among scientists is simply the ocean gas, because on our own planet, it comes almost entirely from marine life. Tiny organisms drifting through the sea release it as a waste product, and over millions of years, it has become one of the strongest known signatures of biology in our own atmosphere. So when this same gas appeared in the atmospheric data of a distant, water-rich planet, it is easy to understand the excitement. Here was a chemical that, on the only planet we know to host life, exists almost exclusively because life exists. Finding it elsewhere felt like finding a fingerprint at a crime scene with no other explanation in sight. Except there was another explanation. Several other explanations, in fact. Laboratory experiments and computer models soon revealed that this same molecule can be produced through completely lifeless chemistry, particularly under high pressure, high temperature conditions involving gases like hydrogen and compounds found in many planetary atmospheres. Some researchers managed to recreate similar chemical signatures using nothing but rock, heat, and gas, no biology required at all. The experiments took months to design and run, since recreating the exact pressure and temperature of a distant planet inside a laboratory chamber is its own difficult engineering problem. This single discovery quietly reshaped an entire field. Astrobiologists, the scientists who study the possibility of life beyond Earth, had to confront an uncomfortable truth. Even a molecule that looks like one of the strongest biological signatures we know is not, by itself, proof of anything. Context matters more than any single chemical. A gas needs to appear alongside other supporting evidence, the right surface conditions, the right combination of companion molecules, before scientists can call it a true biosignature rather than a coincidence of chemistry. Farther still, in the broader hunt for life, this problem multiplies. Multiple potential biosignature gases, ones that excited researchers in earlier years, have each turned out to have lifeless alternate explanations once examined closely enough. Oxygen itself, the gas most associated with life on Earth, can be produced abiotically under the right stellar and atmospheric conditions, especially around certain types of stars. Methane, another hopeful candidate, behaves in much the same frustrating way. This is the quiet, unglamorous reality behind every exciting headline about possible alien life. The chemistry of a lifeless universe is creative enough, varied enough, that it can echo biology without ever producing it. Until our instruments are sensitive enough to detect multiple confirming signals at once, surface features, seasonal changes, several gases appearing together in a pattern that lifeless chemistry struggles to explain, every single detection will remain just that. A possibility, not a confirmation, no matter how exciting the headline reads. It is a warning about how easily the universe can disguise nothing as something, and it forces a harder question. If we cannot even trust a strong chemical signal sitting in front of our best telescope, how much confidence should we really place in the silence surrounding everything else we have not yet examined? At first, a false alarm sounds like good news. No real signal of life means no immediate danger, no philosophical crisis, nothing to upend our place in the universe. But sit with the idea a little longer, and the opposite becomes true. A false alarm is not comforting. It is a warning shot, and it deserves to be treated as one. Here is why. If finding biosignatures were simple, if life left behind clean, unmistakable chemical evidence every time, then a false alarm would just be an unlucky planet, an outlier in an otherwise straightforward search. That is not what we are learning. We are learning that the chemistry of life and the chemistry of lifeless rock and gas overlap far more than expected. The line between a living world and a dead one is blurrier, more easily confused than scientists once assumed. This matters because it means our search tools are less reliable than we hoped. Every planet we have flagged as promising over the last decade now carries an asterisk beside it. Every gas we once treated as a strong clue now needs to be re-examined under harsher scrutiny than before. The universe, it turns out, is an excellent forger. It can paint a convincing portrait of biology using nothing but raw chemistry and time, no living cell required anywhere in the process. Compared to what comes next, even this realization is only the surface of the problem. If non-living chemistry can fake biological signatures this convincingly here, in our own neighborhood of the galaxy, then somewhere out there, the reverse could also be happening. Real signs of life could be hiding behind explanations that look perfectly ordinary, perfectly lifeless, simply because our models are not yet refined enough to tell the difference between the two. This cuts both ways, and that is what makes it unsettling rather than reassuring. It means the silence we have recorded for the last several decades cannot be fully trusted either. Some of what we have dismissed as ordinary, lifeless chemistry might not be. Some of what once excited us as a possible biosignature has already been quietly walked back and may eventually be walked back again in the other direction. We are working with a deeply imperfect filter. We are trying to detect a signal we are not entirely sure how to recognize, using instruments that can be fooled by ordinary geology, scanning a universe that may be accidentally disguising the very thing we are looking for. This is the uncomfortable truth sitting underneath every confident headline about alien life. Science is not lying to you when it gets excited about a new gas in a distant atmosphere. It is doing its job, testing every possibility before settling on an answer. But each time that excitement fades back into uncertainty, it reveals just how poorly equipped we still are to answer the question that matters most. That uncertainty, more than any quiet night sky, is the real source of the disturbing silence we are chasing tonight. Long before modern telescopes existed, scientists tried to put a number on the odds of finding company in the universe. The most famous attempt came from astronomer Frank Drake in 1961, who built a simple equation meant to estimate how many communicating civilizations might exist in our galaxy at any given moment in its long history. The equation itself is almost embarrassingly straightforward. Multiply the rate of star formation by the fraction of stars with planets, then by the fraction of those planets that could support life, then by the fraction where life actually develops, then by the fraction where that life becomes intelligent, then by the fraction that develops the technology to communicate across space, then by how long such a civilization might survive while broadcasting. Multiply all of those fractions together and you get an estimate. The problem, and the reason this equation has fascinated and frustrated scientists for over half a century, is that almost every term in it is still a guess. We have only recently confirmed real numbers for the first two terms, star formation rates and the frequency of planets, thanks to large-scale surveys. The remaining terms, especially the odds that life becomes intelligent and chooses to broadcast, remain almost entirely unknown, leaving plenty of room for wildly different conclusions depending on which assumptions a researcher chooses to plug in. And yet, even using deliberately cautious, conservative numbers for every unknown term, many versions of this calculation still produce a result suggesting our galaxy should currently host dozens, sometimes thousands, of communicating civilizations, Some optimistic versions of the equation, using slightly more generous assumptions, produce numbers in the millions instead. This is where the mathematics collides head-on with our observations. If even a modest fraction of those predicted civilizations exist, some of them should be far older than humanity, simply because the universe itself is far older than humanity. A civilization, even a few 100,000 years more advanced than us, a blink of an eye on a cosmic timescale, could plausibly have spread probes, signals, or structures across enormous distances by now. Compared to what the mathematics predicts, our radio telescopes have heard nothing resembling a deliberate signal. Our space-based observatories have spotted no obvious megastructures, no unmistakable signs of engineering on a planetary or stellar scale. The numbers say contact should be almost routine. Reality, stubbornly, says otherwise. This gap between expectation and observation is precisely what transformed Fermi's lunchtime question into one of the most serious puzzles in modern science. The mathematics, built from real, confirmed astronomical data, suggests life should be common. The silence surrounding all that mathematical promise has never once been broken. And the longer that gap persists, the more it suggests the missing variable in this equation is something far stranger than a number we have simply miscounted. Some researchers now suspect the missing variable is behavioral rather than mathematical, hidden in how civilizations actually choose to act once they reach our level. In 1960, astronomer Frank Drake pointed a radio telescope in West Virginia toward two nearby stars and listened. It was the first serious, scientific attempt to search for an artificial signal from beyond our solar system. He called it Project Ozma, named after the ruler of a fictional, faraway land. He heard nothing unusual, just the ordinary static of the universe, hour after patient hour. That moment opened a search that has continued, in various forms, for over 7 decades. Today, organizations dedicated to this work scan enormous portions of the radio spectrum, pointing increasingly sensitive instruments at millions of stars, hunting for any signal that could not be explained by natural causes. Modern projects can scan more frequencies in a single day than early researchers managed across entire years of careful, patient effort, a difference made possible by decades of steady improvement in computing power and antenna design. And across all of that time, across millions of hours of listening, only a small handful of signals have ever generated real, lasting excitement. The most famous remains a powerful, narrow burst of radio energy detected in 1977, so striking that the astronomer who found it circled it on the printout and wrote a single excited word beside it. Decades of follow-up observation, however, have never managed to detect that signal again, and its true origin remains, to this day, an open and unsolved mystery, rather than a confirmed transmission from another civilization. Every other promising blip recorded over the decades has eventually been traced back to something mundane, passing satellites, equipment interference, even, in one memorable case, a forgotten microwave oven on the research site itself. Each time, hope rose, and each time, a boring explanation followed close behind it. This is a confirmed fact, not a theory. We have searched, seriously and persistently, for 7 decades, using better instruments nearly every single year, and we have never once confirmed an artificial signal from beyond our solar system. That is an extraordinary, sustained absence, one that gets harder to explain away with each passing year of improved technology. Compared to what comes next, even this silence has a strange comfort to it, because, at least it is familiar. Scientists have grown used to the quiet, and many have built entire careers around interpreting it. What troubles the field more deeply is a newer concern, one that has only gained traction in the last couple of decades. What if the search itself has been aimed the wrong way the entire time? What if civilizations far more advanced than us communicate using methods we have not even thought to listen for, leaving our radio telescopes scanning the wrong kind of silence entirely. This idea does not erase 70 years of careful, honest searching. It simply suggests that absence of evidence using one method does not guarantee absence of life using every method. And that distinction becomes critically important as we examine just how easily a real signal could slip through every filter we currently use. Every field of science has a moment that almost changed everything. For the search for extraterrestrial intelligence, that moment happened on a quiet August night in 1977. A radio telescope in Ohio, scanning the sky as part of a routine survey, recorded an extraordinarily strong, narrow signal, one that stood out dramatically from the background noise the instrument normally captured during an ordinary shift, the kind of anomaly that researchers usually dismiss within minutes of seeing it. The signal lasted just over a minute, the exact amount of time the telescope's rotation would allow it to sweep across a fixed point in the sky, which is precisely the behavior expected if a real, distant signal had been detected rather than local interference. Its strength was roughly 30 times stronger than the ordinary background radiation of the sky. When the astronomer reviewing the printout days later saw the data, he circled the signal and wrote a single word that would follow this event for the rest of scientific history. Word of the discovery spread quickly through the small community of researchers searching for exactly this kind of evidence. Here, finally, was a signal that matched almost every expectation for an artificial transmission. It was narrow in frequency, the kind of signal a natural cosmic process struggles to produce. It came from roughly the direction of a distant group of stars, and it appeared exactly once, with a strength and shape that did not match any known satellite, aircraft, or terrestrial source available at the time of the detection. Compared to what should have happened next, the story took a frustrating turn. Despite repeated attempts, using the same telescope and later more advanced instruments, that signal has never been detected again. Not once, not from the same coordinates, not at the same frequency. Modern searches using significantly more sensitive equipment have scanned that same patch of sky many times since, always coming back empty-handed, year after disappointing year. This is an important trust signal worth stating clearly. The event remains, to this day, an unexplained anomaly, not a confirmed message from another civilization. Several alternative explanations have been proposed over the decades, including the rare possibility of a natural astrophysical event or even an undocumented reflection of a terrestrial signal off space debris. But none of these explanations have been proven conclusively either, leaving the case formally open. What makes this case so haunting is not that it proves alien life exists. It does not. What makes it haunting is that it briefly showed exactly what real evidence might look like if it ever arrived, narrow, strong, and gone before we could properly investigate. If a signal exactly like this one passed through our detectors again tomorrow night, lasting only a single minute before vanishing forever, we would face the exact same frustrating outcome. Strong evidence, with absolutely no way to confirm or chase it down. And that uncomfortable limitation of our entire search method becomes the next piece of this mystery. To understand why we might be missing signals from elsewhere, it helps to turn the telescope around and study ourselves instead. For roughly a century, humanity has been leaking radio energy into space, an unintentional byproduct of broadcasting, radar, and modern communication technology. For decades, this leakage was treated as a kind of cosmic calling card, proof that any sufficiently advanced civilization listening nearby could eventually detect us without much effort at all, simply by pointing a sensitive enough receiver in our direction. That assumption no longer holds up well. Our oldest, strongest broadcasts, powerful television and radio transmissions from the middle of the last century, have been weakening and fading as they travel outward, exactly as physics predicts. Radio waves spread out and lose strength dramatically with distance, following a mathematical pattern where the signal weakens with the square of how far it travels. Even our most powerful broadcasts from decades past would be nearly impossible to detect using instruments similar to our own by the time they reached even our nearest neighboring star systems. Modern technology has made this problem worse, not better, in an ironic twist nobody saw coming. Older broadcast television and radio used powerful, far-reaching signals that spread their energy widely across the sky. Newer communication methods, focused satellite transmissions, fiber optic cables buried underground, and tightly directed digital signals are dramatically quieter from an outside perspective. In a strange way, as humanity has become more technologically advanced, we have actually become harder to detect from a distance rather than easier. This is a confirmed and measurable fact, not speculation. Calculations based on the actual physics of radio wave propagation show that an instrument similar in sensitivity to our best current telescopes would struggle to detect Earth's own radio leakage from even a relatively close cosmic distance, let alone from across the galaxy. Compared to what comes next, this realization carries a heavier implication. If our own civilization, despite generating powerful signals for over a century, has already become nearly invisible to instruments like our own, what does that suggest about everyone else out there? Any civilization following a similar technological path, starting with loud, leaky broadcasts before transitioning to quieter, more efficient communication, would only remain detectable for a brief window of time, likely just a handful of decades, before fading into the same kind of practical silence we are now approaching ourselves. This idea has become known among researchers as the short broadcast window problem. It suggests that even if intelligent life is common throughout the universe, the period during which any civilization is loud enough to be noticed might be extraordinarily brief compared to the overall lifespan of a species or a planet. If that window truly is this narrow, then the silence we have recorded for 70 years of careful listening might say almost nothing about how many civilizations exist. It might only reveal how poorly suited our current method is for catching anyone during their brief, noisy adolescence, a phase every civilization may pass through quickly before falling silent again. If radio signals are an unreliable way to search for company, many scientists have shifted their attention towards something more direct, the chemistry of distant planetary surfaces themselves. And here, a new and surprising obstacle has emerged. One involving the very planets we once considered our best candidates for life. The kind of obstacle nobody expected to find waiting in such promising places. For years, astronomers have been especially excited about a particular category of distant worlds, ones significantly larger than Earth but smaller than the gas giants in our own solar system, orbiting cool, dim stars in well-positioned habitable zones. Several of these worlds show strong evidence of water in their atmospheres, an encouraging sign, since water remains the single most important ingredient scientists associate with the possibility of life as we currently understand it. But here is the complication. Many of these promising worlds appear to be almost entirely covered in extremely deep oceans, far deeper than anything found on Earth, with water layers potentially hundreds of times deeper than our own deepest trenches. At first, this might sound like fantastic news for the search for life. More water should mean more opportunity for biology to take hold somewhere within it. Instead, researchers have discovered a troubling possibility hiding underneath all that water. On a planet with oceans this extraordinarily deep, the immense pressure at the bottom can create exotic forms of ice that exist even at warm temperatures, forming a thick barrier between the ocean above and the rocky planetary core below. This barrier would prevent the kind of chemical exchange between water and rock that many scientists believe was essential to how life first emerged on early Earth. Without that exchange, oceans, no matter how vast or how warm, could remain permanently, chemically sterile. This is where trust signals become especially important. It remains an open, unconfirmed question whether deep water worlds like these can support life at all. Some researchers believe limited chemical exchange might still occur under certain conditions. Others believe the barrier created by deep ocean pressure makes life on these particular worlds extremely unlikely, regardless of how much liquid water happens to be present. Farther still, in the search for solutions, scientists have proposed a new method for telling these planets apart from truly Earth-like worlds. By measuring the way starlight reflects off a planet's surface rather than just passing through its atmosphere, researchers believe they could eventually detect the presence of exposed land, continents rising above the waterline. A planet with visible land would suggest a shallower, more chemically active ocean, exactly the kind of environment many scientists believe gives life its best chance to begin. Until instruments capable of this kind of detailed reflection analysis become available, likely requiring an entirely new generation of space telescope, every deep ocean world we have found will remain a tantalizing, frustrating mystery. Beautiful, water-rich, and possibly, despite every encouraging sign, completely and permanently empty of anything resembling life, hiding its answer beneath an ocean we cannot yet see through. It seems almost backward, but in the search for life beyond Earth, scientists have begun looking specifically for dry ground rather than water. The reason connects directly to the deep ocean problem explored a moment ago, and it reveals just how easily a planet can disguise its true potential for life from a distance, sometimes hiding its biggest weakness behind its most exciting feature. Earth itself offers the clearest example of why exposed land matters so much. Roughly 70% of our planet's surface is covered by ocean, yet the remaining dry land plays an outsized role in the chemistry that scientists associate with a living world. Rain falls on exposed continents, washes minerals into rivers, and carries them into the sea, creating a continuous chemical exchange between rock and water that many researchers believe helped life establish itself in the first place, and continues to help regulate the planet's climate and atmosphere today. A planet completely covered in extremely deep water, by contrast, loses access to this entire process. Without exposed rock for rainfall and weather to interact with, the chemical cycles that keep a planet's atmosphere balanced over long stretches of time may break down or never form correctly at all. Some computer models suggest that a planet with deep enough oceans could experience wild, destabilizing climate swings over millions of years, lacking the natural regulating system that exposed continents help provide to a stable world. This creates an unusual contradiction at the heart of modern planet hunting. The very feature that first excites astronomers, strong evidence of abundant water in a planet's atmosphere, might actually be working against the odds of finding life, rather than supporting it. A planet that looks wet and promising from a distance could, upon closer inspection, turn out to be drowning in the very substance meant to support life, lacking the dry, chemically active land needed to make that life possible in the first place. Researchers have proposed a clever method to address this confusion. Rather than only studying the chemical composition of a planet's atmosphere, future telescopes, equipped to study reflected starlight, could measure subtle differences in brightness and color across a planet's surface as it rotates. Oceans, ice, and exposed continents each reflect starlight differently. By carefully analyzing these reflection patterns, scientists believe they could eventually distinguish a planet with genuine, varied terrain from one that is entirely, uniformly covered in water from pole to pole. This remains an unconfirmed, developing area of research, not yet tested on a real distant world, since the technology required does not currently exist in space, but it represents an important shift in thinking. The search for life is no longer just about finding water. It is about finding the right amount of water, balanced against enough exposed land to keep a planet's chemistry alive and active. And that narrower, more specific target makes the already difficult search for company even harder than it first appeared to be, narrowing an already enormous haystack down even further. Up to this point, every obstacle we have examined involves finding or recognizing life. This next obstacle is different. It suggests that even a successful, advanced civilization, one that has already solved every previous problem, might still choose to stay completely silent, and the reason has everything to do with basic physics rather than hiding from anyone watching. The concept centers on something called Landauer's principle, named after physicist Rolf Landauer, who demonstrated a fundamental link between information and heat. Every time a system, whether a brain, a computer, or any device capable of processing information, performs an irreversible calculation, it must release a small amount of waste heat into its surroundings. This is a basic law of physics that applies to any possible form of computation, no matter how advanced the civilization performing it happens to be. Here is why this matters on a cosmic scale. The background temperature of the universe itself is not zero. Even the emptiest regions of space carry a faint residual warmth left over from the early universe, a leftover glow sitting at a few degrees above absolute zero. This background temperature creates a kind of cosmic noise floor, a baseline that any civilization trying to dispose of its own waste heat must work against constantly. The warmer the surrounding universe, the harder and more expensive it becomes to cool down a large-scale computing system, and the less efficient every calculation becomes. Picture trying to run a powerful, heat-generating machine inside a sealed room that is already uncomfortably warm. Every bit of cooling you attempt becomes a fight against the room itself, never fully won. A handful of physicists have proposed something genuinely startling using this principle. Because the universe is gradually, steadily cooling as it expands, a civilization willing to wait might eventually access an extraordinarily favorable cooling environment, one potentially many billions of years in the future, when the background temperature has dropped dramatically lower than it sits today. This single idea, once published, quietly reframed an entire decades-old debate among physicists studying the limits of computation itself. According to calculations published by researchers studying this idea, waiting for that cooler future could allow a civilization to perform an almost unimaginably larger amount of total computation using the very same amount of stored energy compared to attempting that same computation today. This remains a theoretical proposal, built on solid, well-established physics, but applied to an unconfirmed and speculative scenario that no observation has yet tested. Compared to everything we have discussed so far, this idea opens a genuinely unsettling new direction. What if the smartest possible response to existing in a warm, young universe is to do almost nothing at all and simply wait, rather than expand loudly and announce yourself? Farther still down this road of thinking lies an idea so strange, so quietly disturbing, that it could explain the entire silence by itself. An idea that begins with something as ordinary as the heat coming off your own thoughts right now. If the previous chapter felt abstract, consider it from a more personal angle. Your own brain, right now, is generating heat. Every thought, every memory you form, every signal traveling along a nerve cell releases a tiny amount of warmth into your body, which your body then has to manage and release into the air around you. Thinking, quite literally, is not free. It costs energy, and that energy eventually becomes heat that must go somewhere, with nowhere truly free to send it, no matter how advanced the thinker happens to be. Now, imagine scaling that same principle up to the level of an entire civilization, one that has moved far beyond biological brains and into vast networks of artificial computation, the kind many researchers believe any sufficiently advanced society would eventually build for itself. A civilization like that would not just be thinking on the scale of one mind. It would be processing information across entire planets, perhaps entire star systems, running calculations at a scale almost impossible for us to picture clearly. Each one of those calculations, no matter how advanced the technology performing them, still obeys the same basic physics that governs heat in your own skull. Every irreversible computation generates waste warmth that must be released somewhere, and the surrounding environment limits how efficiently that release can happen. A civilization operating inside a relatively warm universe, one still glowing faintly from its early, hotter history, faces a kind of permanent tax on every single thought its systems perform forever. This creates a strange, almost philosophical tension. The smartest, most advanced civilizations, the ones capable of the most extraordinary feats of engineering and computation, might also be the ones most aware of just how wasteful it is to think too quickly, too loudly, too soon, in a universe that will only get cheaper to think in as time goes on. Farther still down this reasoning, some researchers have suggested that an advanced enough society would treat raw computation the way a careful investor treats money, recognizing that patience and timing can multiply the value of every resource spent on it. This idea reframes silence itself. Instead of imagining an empty universe with nothing intelligent left to find, picture instead a universe filled with extraordinarily patient minds, fully capable of communication and expansion, choosing instead to conserve their energy for a future moment when that energy will be worth dramatically more than it is today. It is confirmed physics that heat dissipation becomes more efficient in a colder environment. It remains an unconfirmed, speculative leap to assume real civilizations behave this way in practice. But the logic holds together cleanly enough that serious physicists have taken it seriously, publishing the idea in peer-reviewed journals rather than dismissing it as science fiction. And once you accept even the possibility that this kind of patience could be rational, the entire shape of the silence around us begins to shift into something far stranger than absence, something closer to a choice being made on a timescale we can barely comprehend. This is the moment where the silence stops sounding like an accident and starts sounding like a strategy. In 2017, a small group of researchers connected to Oxford University published a paper with an unusual title, one borrowed from old poetry, suggesting that something which appears dead may simply be lying in wait for a better moment to act. The idea inside that paper has come to be known as the aestivation hypothesis, named after a biological process found in certain animals that enter a deep, protective dormancy during periods of extreme heat, rather than cold, conserving everything until conditions improve. The proposal itself builds directly on everything explored in the last 2 chapters. If computation becomes dramatically more efficient as the background temperature of the universe drops, and if the universe is destined to keep cooling for billions of years into the future as it continues expanding, then an extraordinarily advanced civilization might conclude that the most rational choice available to it is simply to wait, patiently, for a better moment to act, rather than spending its resources too early. According to the calculations published in that original paper, an advanced civilization willing to delay its major computational activity until the universe reaches a much colder average temperature could eventually perform a staggeringly larger amount of total computation using the exact same stored energy, compared to using that energy today. The numbers involved are almost impossible to picture, describing potential gains measured in factors with 30 zeros attached to them. If a civilization accepted this reasoning, it would not behave like the loud, expanding, signal-sending society many people imagine when picturing advanced aliens. It would instead expand quickly and quietly during an early, brief phase, gather the raw materials and energy it needs across its local region of space, and then power down into an extremely low energy, largely passive state, conserving everything for a far distant future moment when the universe finally cools enough to make full use of it. This is, importantly, a theoretical proposal, not a confirmed explanation for anything we observe. The scientists who created this idea have stated openly that they do not necessarily believe it themselves. They built it as a serious thought experiment, a way of testing whether the silence we observe could be explained by something other than absence or destruction, an exercise in rigorous speculation rather than a firm prediction. Other physicists have pushed back directly, arguing that the underlying assumptions about computation and energy may not hold up as cleanly as the original paper suggests. Compared to every other explanation explored so far, this one carries a particular kind of unease. It does not require life to be rare. It does not require civilizations to destroy themselves. It simply requires patience on a timescale that dwarfs human history entirely, a kind of cosmic stillness that would look, from any reasonable human perspective, exactly like the silence already surrounding us tonight, indistinguishable from emptiness, unless you already know what you are looking for. It helps to put real numbers around this idea, even simplified ones, to understand just how seriously some physicists take it. The current background temperature of the universe sits at a few degrees above the coldest, theoretically possible temperature, a leftover glow from the early, hot universe that has been steadily fading as space itself stretches outward in every direction, a fading that has continued, uninterrupted, since the earliest moments after the Big Bang. According to the original aestivation research, this temperature will continue dropping for an extraordinarily long time, with significant cooling occurring across timescales measured in the trillions of years rather than the billions we are used to discussing in ordinary astronomy. From the perspective of a civilization with access to advanced enough technology and a sufficiently long view of its own existence, that future cooling represents an enormous, untapped resource, one that grows more valuable the longer you are willing to wait to use it. Here is the comparison the original researchers offered to make this concrete for the rest of us. According to their estimates, a civilization that waited to perform its computation until the universe had cooled significantly could complete vastly more total calculations using the same stored energy supply compared to performing that computation in the present, warmer era. The improvement factor they calculated runs into the magnitude of 10 followed by 30 zeros, a number so large it stops being intuitive and becomes purely symbolic of how dramatically efficiency could improve. For us, thinking on a human timescale, waiting even a single century feels enormous, but a civilization capable of surviving on a timescale of millions or billions of years might view the situation completely differently. If you already expect your civilization to exist for an immense span of time, choosing to remain quiet and conserve resources for a small fraction of that span, even a fraction lasting many millions of years, might feel like an obvious, almost trivial sacrifice in exchange for an overwhelming future gain. Farther still, this reasoning offers an elegant answer to a question that has bothered scientists for decades. Why would an advanced civilization, fully capable of expanding loudly and announcing itself across the galaxy, choose silence instead? The aestivation hypothesis suggests the answer might simply be patience. Not fear, not destruction, not isolation by force, just a long, calculated decision to remain still until the conditions around them finally became efficient enough to justify acting at all. This remains entirely speculative, an unconfirmed theory built on solid physics but applied to an unproven scenario nobody has tested directly. Yet it forces an uncomfortable question for anyone listening tonight. If the smartest possible response to existing early in a warm universe really is silence, then our 70 years of careful listening may not have failed to find anyone. It may have simply arrived during the part of the story where almost everyone capable of answering has deliberately chosen not to, and may continue choosing that way for a very long time still ahead. There is a meaningful difference between a universe that is empty and a universe that is simply quiet on purpose, and that difference changes everything about how we should interpret the data we have collected so far. An empty universe offers no real surprises hiding anywhere within it. A deliberately quiet universe means surprises could be sitting everywhere, simply choosing not to reveal themselves yet, watching and waiting just as carefully as we are. If the aestivation hypothesis holds even a grain of truth, it reframes every search method explored earlier in this story. Our radio telescopes are listening for loud, active broadcasts, the kind a young, expanding civilization might produce during its brief, noisy phase. But a civilization that has already passed through that phase and settled into a long-term, dormant strategy would produce almost no detectable signal at all. It would not be hiding from us out of fear. It would simply have no practical reason left to make any noise, having already gathered everything it needs. This idea also offers an explanation for something that has puzzled astronomers for years: the apparent absence of obvious large-scale engineering projects anywhere in the universe. If sufficiently advanced civilizations existed and were actively expanding, building massive structures around their stars to harvest energy, we might expect to see unusual patterns in starlight, stars dimming in strange, artificial-seeming ways, or unusual infrared signatures suggesting waste heat from giant engineering projects, the kind of signature a careful survey should be able to catch. Large-scale surveys searching for exactly this kind of evidence have come back almost entirely empty-handed. An aestivating civilization would explain this absence cleanly. Rather than building enormous, energy-hungry megastructures today, while energy remains comparatively expensive to use efficiently, such a civilization might instead construct compact, extremely passive storage systems, holding on to raw energy and resources without actively using them, waiting instead for the far future moment when using that energy becomes dramatically more efficient than it is right now, a moment that may still be unimaginably far away. Here is where the idea becomes genuinely difficult to dismiss as pure speculation. Several of the original researchers proposed specific, testable signatures that future astronomers could search for, evidence of unusual stellar behavior consistent with energy being stored rather than spent, or strange patterns in how certain galaxies appear to be losing raw material without producing the kind of visible activity normally associated with star formation or energy use. This remains, importantly, an unconfirmed theoretical framework, not an accepted explanation for the silence, but it offers something the other explanations in this story struggle to provide: a reason for the silence that does not require life to be rare, does not require constant self-destruction, and does not require us to be completely, tragically alone. It simply requires almost everyone capable of answering to have made the same quiet, patient decision long before we ever arrived to start listening for them, a decision still being honored somewhere out there tonight. If somewhere out there a civilization truly has chosen long-term silence as its strategy, the next obvious question becomes practical rather than philosophical. What, exactly, would we be looking for? And could we even recognize it if it were sitting directly within range of our instruments right now, tonight, without us realizing what we were seeing? According to researchers who first proposed this idea, an aestivating civilization would not look dramatic or obviously artificial from a distance. It would not glow with unusual brightness or radiate excessive heat the way an actively expanding, energy-hungry civilization might. Quite the opposite. A society choosing to conserve its resources for the distant future would likely appear almost boringly quiet, deliberately minimizing any unnecessary activity that might waste stored energy before the optimal moment arrives, decades or centuries or millions of years from now, far beyond any timescale we ordinarily plan around or even think to imagine. One proposed signature involves unusual patterns in how certain regions lose access to raw material over time. If an advanced civilization were systematically gathering and storing matter and energy across an enormous area, perhaps an entire galaxy, astronomers studying that region might notice subtle, unexplained gaps, areas where expected stellar material or energy seems to be missing without an obvious natural cause to point to, almost as if something had quietly swept the shelves clean and left no trace of how it happened or why it chose that particular region. Another proposed signature involves extremely cold, technologically engineered structures, systems specifically designed to operate at temperatures far below their natural surroundings, minimizing waste heat as efficiently as physically possible. Detecting something this deliberately disguised would require extraordinarily sensitive infrared instruments capable of distinguishing a genuinely engineered cold structure from ordinary, Naturally cold objects like dust clouds or distant inactive stars scattered through the same region of space. An extremely difficult task, even with the best telescopes we currently have. Here is an uncomfortable trust signal worth stating plainly. As of right now, no confirmed candidate matching either of these proposed signatures has ever been found. This remains a purely theoretical search target, a list of clues astronomers could look for, rather than a list of discoveries already made and confirmed by independent observation across multiple research teams. Compared to everything explored so far, this idea quietly reframes one of the most basic assumptions behind the entire search for company in the universe. We have spent 70 years assuming that an advanced civilization would want to be found, would broadcast loudly, would build visibly enormous structures advertising its own existence to anyone listening. The aestivation hypothesis suggests the opposite might be true for the most advanced civilizations of all. The smartest, most patient societies in the universe might be the very ones working hardest to remain completely, deliberately invisible, out of nothing more than careful, long-term planning, stretched across a length of time we can barely begin to imagine, let alone search for with confidence. Some of the strongest hints supporting unusual explanations for the silence have not come from radio telescopes at all. They have come from simply counting things and noticing what should be there, but isn't anywhere in the data, no matter how carefully astronomers look for it. In the early 21st century, a research project specifically searched a massive portion of the visible sky looking for an unusual kind of signature, infrared heat, suggesting an advanced civilization had built a structure large enough to surround its own star and harvest its energy directly, a concept first proposed decades earlier by physicist Freeman Dyson and still studied seriously by astronomers today. If such a structure existed, it would block most of the star's visible light while still radiating detectable waste heat outward as infrared radiation into the surrounding darkness. This search, examining roughly 100,000 galaxies, found nothing definitively matching what an artificial megastructure should look like. No unexplained infrared excess consistent with a Type 2 or Type 3 civilization, the kind capable of harnessing the energy of an entire star or an entire galaxy, appeared anywhere in that enormous dataset. Despite careful, repeated checking, this is a confirmed result, not a guess. Across that survey, and several others conducted using similar methods since, the universe has shown no obvious evidence of galaxy-spanning engineering on the scale many theorists once expected an old, advanced civilization to eventually produce somewhere in its long history, anywhere within reach of our instruments. Some researchers have pointed to this absence as quietly significant. If even a small fraction of galaxies, just a handful out of the 100,000 studied, contained a sufficiently advanced civilization actively expanding and harvesting energy on a massive scale, that activity should have been detectable using current methods. Finding nothing at all across a sample that large places a real, measurable limit on how common such loudly expanding civilizations can possibly be, at least within the portion of the sky this particular survey was able to cover. Compared to assuming this proves we are alone, a more careful reading of this evidence opens a different door entirely. It does not rule out quiet civilizations, only loud ones. It does not rule out a society that has already passed through its brief, expansive phase and settled into a long-term, deliberately low-energy state, exactly the kind of behavior the aestivation hypothesis predicts. A truly patient civilization would, by design, leave behind almost none of the signatures these surveys were built to detect in the first place, no matter how carefully astronomers searched. Farther still, in the broader picture forming across this entire investigation, the absence of loud, obvious civilizations begins to look less like proof of emptiness, and more like a clue pointing toward a universe filled with quiet, careful, long-term thinkers, intentionally leaving as small a footprint as possible while they wait for a future far beyond anything we can currently measure with our instruments, however sensitive they eventually become. Even setting aside questions of patience and dormancy, the universe presents a far more basic, almost mechanical obstacle to contact, one rooted simply in how space itself behaves at the largest scales imaginable. The universe is not static, it is expanding, and that expansion is happening everywhere, all the time, stretching the distance between every galaxy a little further apart with each passing moment, whether anyone is watching or not. This expansion creates a genuinely strange problem for any civilization hoping to reach across cosmic distances. As space stretches, distant galaxies are not just far away, they are actively moving farther away, in many cases faster than light could ever cross the growing gap between us and them. This does not violate the laws of physics, since it is space itself expanding rather than any object moving through space, but the practical effect is the same. Beyond a certain distance, contact becomes mathematically, permanently impossible, no matter how advanced the technology involved happens to be, even with unlimited time to attempt it. Confirmed astronomical measurements show that this boundary, often called the observable universe's edge, already excludes an enormous portion of all existing galaxies from ever making contact with us. Regardless of how much time passes or how advanced anyone becomes, no matter how clever their technology eventually grows, civilizations existing beyond that boundary are not silent by choice. They are silent because the universe itself has physically separated us beyond any possible recovery, forever. Compared to this distant boundary problem, an even more local version of the same issue exists much closer to home. Even within our own galaxy, real, communicating civilizations face an enormous timing problem layered on top of pure distance. Sending a radio signal to a star 1,000 light-years away takes 1,000 years to arrive, and any reply would take another 1,000 years to return. A meaningful, back-and-forth conversation across galactic distances would unfold across timescales longer than entire human civilizations have existed. This timing problem alone could explain a significant portion of the silence we have recorded without requiring rarity, self-destruction, or deliberate hiding of any kind. Two civilizations could exist at the exact same moment, both actively broadcasting, both genuinely curious about contact, and simply miss each other entirely because their signals require so many thousands of years to cross the space between them, arriving long after either civilization has changed beyond recognition. Farther still, this problem compounds with everything explored earlier in this investigation. A civilization following the aestivation strategy, choosing long stretches of patient silence, combined with the simple physical reality of expanding space and enormous transit times, creates a universe where successful contact requires an almost impossible alignment of timing, distance, and intention, all occurring simultaneously, across distances that already strain the imagination. The silence, under this lens, stops looking unusual at all. It starts looking like the expected, ordinary outcome of existing inside a universe this vast and this indifferent to convenient timing. To understand just how narrow the window for contact really might be, consider every requirement explored so far, stacked together rather than treated separately. The way a detective lays out every clue side by side before drawing a conclusion. A civilization needs to exist on a planet within the right habitable zone. That planet needs the right combination of land and water, avoiding the deep ocean trap explored earlier in this investigation. Life needs to emerge, survive billions of years of stability, and eventually develop intelligence capable of building technology. That civilization then needs to pass through its brief, detectable broadcasting phase, the relatively short window before quieter, more efficient communication technology renders it nearly invisible from a distance, exactly as has already begun happening to humanity within the span of a single century. And if the aestivation hypothesis holds any truth, that same civilization eventually needs to make the deliberate choice to remain active and detectable, rather than settling into a long, patient silence to conserve resources for the distant future. Now, Place all of that timing requirement against the backdrop of an expanding universe, one where distant signals take thousands or even millions of years simply to cross the gap between two potential civilizations. For genuine contact to occur, two separate civilizations need to be in their brief, loud, detectable phase at the same approximate cosmic moment, close enough in space that a signal could realistically cross the distance within a meaningful span of time for either side to notice. When you multiply every one of these narrow conditions together, the mathematics shifts dramatically. It is entirely possible for the universe to be filled with intelligent life across its long history, civilizations rising and falling across different corners of different galaxies at different times, and for almost none of them to ever overlap in both timing and detectable behavior simultaneously. This idea has become known among researchers studying this problem as a timing-dominated solution to the silence, distinct from explanations relying purely on rarity or self-destruction. It suggests company could be common throughout cosmic history, while still making confirmed contact between any two specific civilizations extraordinarily rare, simply due to the scale of time and space separating any two potential candidates from each other. Farther still, this framing changes how we should interpret our own 70 years of careful listening. It is not necessarily evidence that no one else exists. It may simply be evidence that our own brief, noisy window happens to be occurring during a moment when no other detectable civilization's window currently overlaps with ours, anywhere within practical reach of our current instruments. This remains an active area of serious research, not a settled conclusion, but it offers a genuinely unsettling possibility, one stranger than simple emptiness. A universe that has always been full of company, consistently missing every possible connection, purely because of timing, century after century, galaxy after galaxy, with nobody ever quite arriving at the right moment to be heard. Step back from distant galaxies for a moment and consider something closer to home, something genuinely uncomfortable to sit with tonight, something that has nothing to do with telescopes at all. Every single piece of evidence explored across this investigation eventually circles back to the same uncomfortable question, one that applies just as directly to humanity as it does to any hypothetical alien civilization elsewhere in the universe. If intelligent life really does follow a somewhat predictable path, emerging from simple chemistry, developing complexity over billions of years, eventually producing technology capable of detectable broadcasting, then every civilization following that same path faces an identical set of tests along the way, regardless of where in the galaxy that civilization happens to arise. Survive long enough as simple life to develop complexity. Survive long enough as a technological society to avoid self-inflicted catastrophe. Decide, eventually, how to behave once technology reaches a level capable of either loud expansion or quiet, patient conservation. This is where the investigation stops feeling like a story about distant aliens and starts feeling uncomfortably personal. Humanity currently sits at one of the most dangerous, uncertain stages along this entire path, a stage many researchers believe could last only a few more centuries before being resolved one way or another. We have already developed technology powerful enough to end our own civilization through several different methods: nuclear conflict, engineered biological threats, or unpredictable consequences from artificial intelligence systems advancing faster than our understanding of how to control them safely. Confirmed historical record shows that humanity has already come dangerously close to large-scale nuclear conflict on at least a few documented occasions during the last century, moments where deliberate restraint, sometimes from a single individual making a difficult decision under enormous pressure, prevented catastrophic escalation entirely. This is documented history, verified across multiple independent sources, not speculation or exaggeration for effect, and it shows just how thin the margin for survival can sometimes be. Farther still, in the broader context of everything explored in this investigation, this uncomfortable parallel suggests something important. If a barrier truly exists somewhere along this path, one capable of explaining why a universe filled with promising conditions remains this quiet, that barrier may not be unique to alien civilizations at all. It may simply be a universal challenge, one every sufficiently advanced society eventually has to face, including, right now, us, here, tonight, listening for an answer that may depend on choices we have not made yet. This single realization is precisely why researchers like astronomer Carl Sagan and economist Robin Hanson took this question so seriously decades ago, and why modern researchers continue studying it today. The silence surrounding us is not just a curiosity about other worlds. It may be a warning sign about our own, one worth understanding clearly before we assume our own story will turn out any differently than everyone else's apparently has, and one worth taking seriously while we still have time to act on it. In 1996, economist Robin Hanson formalized this uncomfortable idea into a concept that has since become one of the most discussed explanations for the silence surrounding us, one that has shaped serious academic debate for decades since. He called it the Great Filter, a theoretical barrier somewhere along the long path from simple chemistry to a galaxy-spanning civilization, one difficult enough that almost nothing manages to pass through it successfully across the entire history of the universe. The logic behind this idea is uncomfortably elegant. If the universe truly contains the enormous number of potentially habitable planets suggested by modern astronomical surveys, and yet remains completely silent despite 70 years of careful searching, then somewhere along the long chain of steps required to become a detectable, expanding civilization, something is stopping almost everyone from making it all the way through to the other side, no matter how many planets get the chance to try. This creates exactly two possible scenarios, and the difference between them matters enormously for humanity's own future, perhaps more than any other open question in modern science. In the first scenario, the filter sits behind us, somewhere in our deep evolutionary past, perhaps the very emergence of life itself. The jump from simple chemistry to the first living cell is so extraordinarily rare that it almost never happens anywhere else. If true, this would actually be reassuring news for humanity. It would mean we have already survived the hardest part, and our future, while never guaranteed, would not be burdened by some unavoidable, universal catastrophe still waiting ahead of us. In the second scenario, the filter sits ahead of us, somewhere in our near future rather than our distant past. This would mean that life and even intelligence might be relatively common throughout the universe, but something consistently, reliably destroys or halts civilizations once they reach roughly our current level of technological development before they ever manage to spread convincingly across their own galaxy, no matter how promising their early progress might have looked. This second scenario is the one that troubles serious researchers the most. It would mean that every other civilization that ever reached our current stage of development, every single one capable of building radio telescopes and asking the same questions we are asking tonight, eventually ran into the exact same wall and failed to get past it every single time across every corner of the galaxy where such a civilization might have arisen. Farther still, this is where the investigation becomes genuinely personal rather than purely academic. If a barrier this consistent and this effective truly exists, humanity is very likely approaching it right now during this exact narrow window of history. And the most unsettling part of this entire theory is that we currently have no way of knowing, with any real confidence, which of these two scenarios actually describes our situation tonight, leaving us to guess at the answer while we keep building the very technology that might decide it. There is a third possibility sitting quietly between the two extremes explored in the previous chapter, one that researchers have only taken seriously in more recent years as our understanding of the universe's history has improved dramatically over the last several decades. The filter may not be behind us or ahead of us in the way originally imagined. It may simply be a matter of timing, a question of when rather than whether. This idea suggests that the conditions necessary for complex, intelligent life may not have existed evenly throughout the entire history of the universe. Early generations of stars contained far fewer heavy elements, the kind of material needed to build rocky planets, complex chemistry, and eventually life itself, since those elements only form deep inside stars and get scattered outward when those stars eventually explode. It took billions of years of repeated stellar explosions, scattering heavier elements progressively further out into the universe, before planets like Earth, rich in the right raw materials, could even begin forming in large numbers anywhere. If this reasoning holds true, intelligent civilizations may not be rare in an absolute sense at all. They may simply be early, among the very first generations of life capable of existing anywhere in cosmic history, rather than one of countless examples scattered evenly across billions of years. Under this scenario, the silence surrounding us would not represent failure or filtering at all. It would represent simple, unavoidable timing, the natural result of being among the first arrivals at an extraordinarily early point in an unimaginably long cosmic story still mostly ahead of us, with most of its chapters yet to be written. This idea offers something genuinely different from every other explanation explored tonight. It does not require humanity to have already survived some impossible filter, and it does not require some terrible barrier still waiting ahead of us in the near future. It simply suggests that intelligent life, including our own, might be arriving close to the very beginning of when such life first becomes possible at all, rather than arriving into an already crowded, ancient cosmic neighborhood filled with civilizations far older than anything we could imagine. Farther still, this idea connects surprisingly well with the patient, aestivating civilizations explored several chapters ago. If being early really does describe our situation accurately, then any other early civilizations elsewhere in the universe would be facing the exact same young, comparatively warm cosmic environment we currently inhabit. The same environment that researchers exploring computational efficiency suggested might favor long-term patience over immediate, loud expansion. This remains, importantly, one possible explanation among several, not a confirmed answer to anything, but it offers something the previous explanations could not. A version of the silence that requires neither universal failure nor permanent isolation. Just an early, narrow moment in an extraordinarily long story, one where almost everyone capable of eventually answering simply has not had enough cosmic time yet to do so, with billions of years still ahead for that to change. Set aside, for a moment, every theory explaining the silence, and consider instead what would actually happen if that silence broke tonight, suddenly and unmistakably, with no warning at all, and no time to prepare for what it would mean for the rest of human history. This thought experiment reveals something important and genuinely unsettling about why the search for contact carries weight far beyond simple scientific curiosity. Throughout human history, every significant encounter between a more technologically advanced civilization and a less advanced one has followed remarkably consistent, often difficult patterns here on Earth itself, patterns documented across continents and centuries. Confirmed historical record shows that contact between dramatically different levels of technology has frequently resulted in serious disruption for the less advanced group, regardless of the intentions held by either side at the time, and regardless of how carefully that contact was managed by the more advanced party involved. Apply that same uncomfortable pattern to the scale of an entire planet, encountering a civilization from somewhere beyond it, and the philosophical stakes become enormous almost instantly. Even a clearly peaceful, scientifically curious message arriving from another civilization could fundamentally reshape human society, religion, politics, and our basic understanding of our own place in the universe, regardless of how carefully that message was intended to be received by whoever sent it across such an enormous distance. Some researchers have argued this is precisely why advanced civilizations, if they truly exist, might choose extreme caution before making contact with a younger, less developed society like our own. This idea connects directly to an earlier theory explored briefly in this investigation, sometimes called the zoo hypothesis. The possibility that more advanced civilizations deliberately avoid contact with developing societies, allowing them to mature naturally without the disruption that early contact might cause to their culture, their confidence, and their sense of their own place in a much larger story still unfolding around them. Compared to assuming malicious intent or deliberate isolation, a simpler, more mathematical explanation may fit better alongside everything else explored tonight. If the patient, estivating civilizations discussed earlier, truly exist, choosing long-term silence for purely practical, computational reasons rather than protective ones, then contact with a younger society, like ours, would represent an unnecessary, wasteful use of resources during exactly the period such a civilization is trying hardest to conserve them. A cost no rational, patient mind would choose to pay so early. Farther still, this quietly reframes the entire emotional weight carried by humanity's continued silence tonight. We are not necessarily being avoided, hidden from, or judged unworthy of contact by some distant, watchful intelligence. We may simply be early, quiet observers ourselves, existing during a narrow window where almost everyone capable of answering has equally practical, equally rational reasons of their own for choosing not to speak first tonight, the same reasons we might choose ourselves if our positions were somehow reversed, and the same patience we might one day extend to someone younger than us. Throughout this entire investigation, we have focused heavily on what we have failed to hear from others. It is worth turning that lens back toward ourselves one final time, because humanity has already, whether intentionally or not, begun sending its own signal into the surrounding darkness, and the shape of that signal reveals something important about our current moment in this entire story, a moment that may be far shorter than we realize. For roughly a century, our planet has leaked increasingly complex radio energy outward in every direction, a confirmed, measurable fact resulting from decades of broadcasting and communication technology. As explored earlier, this leakage has already begun fading as our technology shifts toward quieter, more efficient methods, meaning our brief window of accidental visibility may already be narrowing even as you listen to this tonight, closing a little more with every passing year of progress we make. Beyond accidental leakage, humanity has also made a small number of deliberate attempts at communication, intentional messages designed specifically to be understood by an intelligence very different from our own. In 1974, scientists used a powerful radio telescope to send a structured, mathematically encoded message toward a distant cluster of stars, describing basic information about our solar system, our biology, and our location, using simple binary patterns intended to be decipherable by any sufficiently advanced recipient who might one day receive it, however long that reception ultimately takes. That message will not arrive at its intended destination for tens of thousands of years, a sobering reminder of just how enormous the distances involved in this entire search truly are. Even if every theory explored in this investigation is wrong, even if intelligent life is common and curious and actively listening, the simple, mechanical reality of cosmic distance means any reply to our own deliberate signals remains, at minimum, tens of thousands of years away from ever reaching us, long after everyone alive tonight has been forgotten. Farther still, this raises an uncomfortable mirror to everything explored tonight. We have spent decades wondering why no one has answered us, while quietly becoming less detectable ourselves with each passing year of technological progress. If another civilization somewhere is experiencing this exact same narrowing window right now, both of us may be in the process of becoming permanently unreachable to each other through the ordinary, unremarkable progression of technology, making each of us quieter over time, rather than through malice or destruction of any kind, a quiet ending neither side would ever choose deliberately. This is the quiet, almost melancholic shape hiding underneath this entire investigation. The silence may not be a single, dramatic answer waiting to be discovered. It may simply be the ordinary, expected sound of an enormous universe filled with civilizations, each moving through their own brief, narrow window of visibility, almost never managing to overlap with anyone else's at all. Two ships passing in a fog too thick and too vast for either one to notice the other. After everything explored across this investigation, here is where all of these threads finally come together. The silence surrounding humanity is not a single mystery with a single, clean, simple answer waiting to be found. It is a convergence of several genuinely plausible explanations, each one chipping away at the assumption that contact should have happened by now, and each one adding its own weight to a much larger, much stranger picture that no single theory could explain alone. Biosignatures we once trusted, like the ocean gas detected on a distant water world, have turned out to be far less reliable than hoped, easily mimicked by ordinary, lifeless chemistry. Water-rich planets that once seemed promising may instead be hiding sterile, pressure-locked oceans beneath their encouraging exteriors. Our own broadcasting window, the brief period during which Earth has been loudly detectable, is already narrowing as our technology grows quieter and more efficient with every passing year, just as it likely has for everyone else who ever tried before us. Layered on top of these practical search problems sits something far stranger, the genuine possibility that the smartest, most advanced civilizations in the universe might rationally choose long-term silence and patience over loud, immediate expansion, conserving their resources for a distant, dramatically more efficient future. Layered on top of even that sits the simple, mechanical reality of an expanding universe, one where distance and timing alone could explain enormous stretches of silence without requiring rarity, self-destruction, or deliberate avoidance of any kind. Three entirely different explanations quietly reinforcing one another. Here is the confirmed truth sitting underneath every theory explored tonight. We genuinely do not yet know which explanation, or which combination of these explanations, accounts for the silence we have recorded across 70 years of careful, honest searching. This remains one of the most significant open questions in modern science, simply because the universe itself has made this particular question extraordinarily difficult to answer with any real confidence. No matter how many new instruments we build to try, year after careful year, what this investigation reveals, more than any single dramatic conclusion, is how deeply this question connects back to our own uncertain moment in history. Whether the answer turns out to be a filter we have already survived, a filter still waiting ahead of us, simple timing across an ancient and patient universe, or some combination none of us have considered yet, humanity currently sits in a uniquely important position to find out for itself. Watching the same sky every other civilization before us may have once watched too, asking the same question in the dark. We are listening, right now, during exactly the kind of narrow, brief window every theory in this investigation suggests matters most. And whatever the true answer eventually turns out to be, one thing remains certain tonight: the silence above you is not empty. It is full of questions, patiently waiting, just like we are, for someone, somewhere, to finally break it.